Thanks for having me, and thanks for the very nice introduction. And it's nice to be back at Stanford after 2 years. And this is actually my first academic travel ever since the pandemic, right? So it's definitely feel very excited to talk to a live crowd rather than just my computer screen. And today I'm going to talk about object skills and the quest for compositional robot autonomy. So as Jeanette introduced, I started my faculty at UT Austin, and I founded a new lab called Robot Perception and Learning Lab there at UT Austin. And so today what I'm presenting are really the first batch of work from my own student, right? So I should start by first saying that I'm very proud of my students' work, and especially during this very difficult time. And because they did this amazing work that I got the chance to talk about them, all right? So let's get started. One of the most exciting news, I think, in the robotics world recently comes actually from the outer space. Right? So maybe some of you already know that James Webb Space Telescope is now successfully launched and fully in operation. So to me, this is really a remarkable progress of robotic system engineering. Right? So out of the thousands of different tasks to be done, there are 300 of them are single point failure. That means that if any of these 300 tasks fails, the entire telescope will fail as a whole. And also because this is in outer space, there's no way that we can send a technician to go fix those bugs. But still, this is a ginormous effort. Right? It takes over $9 billion in terms of money, and a huge team of engineers and scientists working together for 20 years. But in the end, it was a great success, and it is successful. So just seeing this news kind of make me wonder that apparently humankind has already figured a way to build extremely complicated yet highly reliable systems. But why we see from the news and social media that autonomous driving cars and personal robots are always 5 to 10 years away? Well, one of the key reasons is that we need a generalist robot to sense and act in the real world. And it is kind of difficult to program and design this robotic system in the traditional form of system engineering. And that's why our research on robot learning come into picture. Right? So it offers a new paradigm to design robotic behaviors with AI and data-driven techniques that are otherwise hard to manually engineer. Typically, when we do robot learning research, the workflow is like this, right? So we have a small team of researchers and faculties and work together, bring some ideas, and this is actually showing me doing research with some of my Stanford colleagues when I was still here. And we come up with this idea, and then we kind of implement the model in our favorite framework, let it be PyTorch, TensorFlow, JAX, and then we try it on our robot platform. If we get a decent success, say 70%, 80% success, and beat all the baseline of our choices, we are pretty happy about it. And then we write a paper, and we get it published in a top conference, and then we move on. And then when we move on to the next work, it is very often that the next paper will not build upon the prior ones, right? So there's no effort taken to get that 70% success to the 99.999% reliability for real-world execution. So we see a dichotomy here. On one side, we know the drill of how to build really complex yet reliable special purpose robotic systems, like the Space Telescope. On the other hand, we see that AI-powered robot learning has become a new paradigm to kind of design and general purpose robotic behaviors in the wild. But the lack of reliability of these learning methods is really preventing us from widespread deployment. So naturally, we are asking, can we combine the best of both worlds? So on one hand, we have this rigorous engineering principles to design complex and reliable system. On the other hand, we can have the robot learning techniques and developed recently to encourage a general and robust behaviors. And that's exactly what I argue as the key to achieve deployable robot autonomy in the wild. So to think about what exactly are the kind of engineering principles that we can learn as a robot learning researchers, I think there's two principles that inspired my research, our research a lot, that are abstraction and composition. What is abstraction? Abstraction concerns about the division of labor. If we give you a very complex system or a very hard problem, how can we break that down into some simpler pieces so that we can work on these individual subproblems in isolation? And what about composition? Is when we piece together these individual modules, right? And how can we make sure that these individual modules work in harmony, in coordination with each other towards this shared and overarching goal? So our recent research has been looking at how can we kind of embrace this engineering principles for building complex robotics system in building general purpose robot autonomy in the world. So if you take a system perspective to look at robotics, generalist robots, that is a complex system that sense and act, right? So there's a sensing to action loop that the robot receives the perceptual information from the environment using its onboard sensors and process the information to determine what's the action to take. And then the action in turn generates new sensory stimuli for the next time's decision making. And a straightforward way to model this sensing action loop is direct mapping, right? So from sensory data to motor actions, if you take a computational perspective, this is a very nonlinear complex function that we can learn. And this is indeed what like this end-to-end deep learning approach has been exploring. Sometimes we call it a pixel to torque, that we learn a direct mapping from the raw sensory data to motor command. And this has been achieving a lot of great progress and impressive demos in recent years, but more and more we start to see the shortcoming of this approach in the kind of the high data requirement, high sample complexity, as well as the brittle generalization. So instead of seeking this pixel to torque approach, or like a research investigator, how can we embrace the principle of abstraction and composition? In particular, how can we learn state abstractions from the raw sensory data? How can we learn the action abstraction from the low-level motor control? And once we establish these two abstractions, we're able to build more robust, like a decision-making modules that achieve a higher level of robustness and generalization. And I call this the compositional robot autonomy stack. So today's topic, I'll talk about the kind of concrete research problem we've been looking at, like in the overall theme of a compositional robot autonomy stack. In particular, we look at how can we build understand unstructured things as a composition of the objects present in the thing. And how can we understand the robotic behaviors as a set of like a skills or repertoire of skills such as grasping, pushing, reaching as a building blocks to synthesize long-term robot interaction. And as an early showcase of this compositional paradigm is our work on neural task programming that I did a while ago with some of my Stanford collaborators here, where the high-level idea is to interpret a long-term robot execution, like say a long-term demonstration sequence of a robotic task, into this hierarchical program, such that a complex procedures like stacking a bunch of color cubes can be recursively broken down into simpler pieces, like stacking a bunch of color cubes can be breaking down to picking a bunch of pick and place actions. And then each pick and place can be further decomposed into picking and placing, and then eventually the pick and place got mapped to some lower level APIs that can be directly executed on the robot. And with this, the objects in these domains are the color cubes on the table, and the skills are picking and placing. And we show that with this object and skill abstraction, we can achieve a higher level of generalization that once our model is trained, we can apply this to generalize to unseen block configurations that never appeared in the training set. So that's much better than the end-to-end approach that we demonstrated earlier. But there's a catch here, that for NTP, the objects and skills are clearly defined, right? So, and very often the cases in empirical study of the compositional approach, we find that this type of a composition modeling typically works really well if we have a clear notion of a finite set of objects and skills and to model. So in the block world and if we're doing a bunch of picking and placing on color cubes, it makes it so easy what's the compositional structure will emerge. But really, the question is, how can we unblock the block word, right? So pun intended here. So when it comes to real world, what are the kind of complete set of objects, and what are the complete set of skills to model in order to really operationalize this compositional approach? That is a kind of fundamental questions. In many research domains, we kind of sweep that under the rug, and we assume that the object and skills are given. That makes it easy to build this compositional approach. But really, I think these are the kind of really fundamental questions to really take advantage of this compositional modeling. So, like, what is an object? What is a skill? Right? So this seems a trivial question from the first look, but the more you think, the more you research, you find that the more you know, the less you know. So really, the questions and the focus of today's talk is to really understand what is the object and the skills to unlock this type of compositional modeling in the stack, autonomy stack. In particular, I'm going to talk about kind of two lines of work on learning object abstraction and skill abstraction. So instead of seeking a universal definition, what is the true definition of a skill and object, we're going to study this in a pragmatic approach. I'm going to study them operationally in concrete problems in robot learning, such that hopefully by studying this, it will give us good intuition. What are the object and skill representation are useful and necessary for building general purpose robot? So for the first one, I'm going to look at like a learning object abstraction from embodied interaction. And then we're going to move to skill abstraction at the second part. Okay, so we study object representation first in the task of robotic grasping. Why robotic grasping? It's very important, like a first skill to learn to unlock a lot of real world applications like assembly, logistics, smart warehousing, etc. Where the input we're assuming is like partial point cloud of the entire thing, and you want to determine the grasp pose and grasp orientations to execute the grasp. Our intuition is that if you look at object, how can we kind of characterize a real-world object? There's different perspectives, like drawing inspiration from human cognition. We can describe an object like a mug. What makes a mug based on its visual attributes, right? So what makes a mug is because it looks like a mug, it has an empty inside, it has a curvy handle. So when we recognize this visual appearance, and we see this is a mug. And an alternative way to look at how we characterize objects is based on their functional properties. Although, no matter how the mug looks like, and the mug is a mug because we can use it to grasp it from the handle, and also it can hold water that we can drink from the mug. So based on this different characterization of objects, it requires different type of understanding of the object geometry versus object affordance. Affordance means the functional properties of the objects. And so our insight is that the object affordance understanding and geometry understanding are not two isolated problems. So when it comes to like encoding object information and building object representation, they're really the two sides of the same coin. So just to use this example to illustrate like this intuition. If we think about how to grasp this mug from this partially observed view, you see that there's a handle that's like a partially occluded. If we want to grasp this mug from this view, if a robot can reconstruct this mug from this partial view, it will help it determine the precise grasp location, grasp orientation to be able to grasp the mug successfully. And once the robot was able to pick up the mug, and that actually confirms the 3D reconstruction, right? So it tells us that there's indeed certain 3D geometry that exists in this occluded area. So it goes the other way. So that means that there's some kind of synergistic relationship between the understanding the geometry, like 3D reconstruction, and the understanding the functional properties, being able to grasp the object. So we built GIGA to capture this intuition, which stands for grasping via implicit geometry and affordance, where the idea is to learn a shared object representation through a 3D backbone and train for both tasks of object affordance and the 3D reconstruction, so that the learned object representation encodes the object information from both dimensions. So the first question we need to answer is, what is a good representation for the object things that encodes affordance and the 3D geometry? So motivated by advances recently from 3D vision and graphics community, we use the neural fields for 3D thing. What is a neural field? Right? So it is a coordinate-based neural network that maps some input feature, like a visual feature of the object, and also occurring coordinates in the Cartesian space XYZ to some quantities at that location, where the quantity can be the size distance function or the occupancy at that location. Why do we like about neural fields? It's because that by encoding the 3D shape as part of the neural network parameters, it allows us to develop this smooth and continuous representation of the things that we can query the coordinates at arbitrary resolution. And also, because this is a differentiable layer, so we can plug that in as part of a bigger network and train with a rich source of supervision, so that encourage multitask learnings to give rise to the meaningful representations from different sources of training data. So that's the key idea. We have the neural fields as a backbone, and to really operationalize this idea, we start with TSDF. That's something we can get from the depth camera on the robot. And then we perform convolution to map this input TSDF into a structured volumetric feature grid. From this feature grid, we can, at each location, we can get a local feature by pulling from the grid and doing some interpolations to get that local feature at a particular point. Based on the local feature and grasp center, we can predict the grasp quality, grasp gripper orientation in that a gripper center. And also, we can query the 3D geometry, like the occupancy probability at the location. And then by training both grasp affordance and the 3D reconstruction with the shared structure feature grids, it encourages information sharing, right? So to be able to encode the objects in both different properties. And to actually train this model, we use a self-supervised procedure. So the way we do that is we dump a rich set of 3D objects into simulating environments, and we sample a variety of a grasp candidate. You can imagine that if we're doing random sampling, some of them will lead to success, others will lead to failure, right? So that will give us a data set of positive and negative data to train the affordance prediction without any human supervision. Okay, so to show how this works and kind of qualitatively on the robot, and this is achieving a state-of-the-art performance on the task of 6-DoF grasping in clutter environment. And typically in my lab, when I ask my students to do real robot experiment, I ask them to show me the uncut video, right? So this is just showing you that a 10-minute continuous execution of robot. Here is Ethan. He's putting a bunch of objects into the thing and running continuous for 10 minutes. You can see that some of the grasp fails occasionally, but overall it has pretty consistent performance in being able to picking up objects from clutter and then drop them into the bin. Okay, so encouraged by this result, so we try to understand why exactly GIGA works and what exactly the object representation learns. All right, so because we are using this implicit neural representation or neural fields, we can actually query the affordance as arbitrary locations in the thing. So by querying the location densely, it allows us to map the 3D thing into this kind of beautiful heat map and called affordance landscape, basically showing what is the grasp quality or grasp success likelihood at each individual locations, where the red one means higher affordance, more likely to have a grasp success. The like the white one or gray ones are low affordance scores. Right? We see that compared to VGN, the former state of art, and our method was able to generate more diverse graphs, and especially in those occluded locations. And to show you qualitatively how that comparison looks like, VGN fails at 2 consecutive trials on picking up the big object. We see that GIGA actually first pick up the small object from behind because it knows that picking up those objects actually is less likely to incur collision. So it was able to declutter these things successfully. So then we kind of take a step further to see what exactly is a 3D shape that's encoded in that representation. So the way we investigate that is we have a 3D reconstruction branch, right? So we can read out the 3D shape, and you can query that occupancy probability at different locations from marching cube to extract mesh from it. And we can actually visualize the mesh and do comparison. And we compare GIGA with 2 different variants. One is only trained with affordance, one is only trained with grasp supervision, and then our final model trains on both. We see an interesting result that the GIGA representation that trained on the grasp affordance actually pay more attention to the graspable part of the thing than the non-graspable part, which kind of makes sense. If you're looking at the 3D reconstruction with only the 3D reconstruction supervision, it sometimes misses some geometric details like the handle of the mug because it's really a thin part of the thing. But when we train with the grasping supervision, it actually tries to reconstruct something, right? So in the graspable part, like a handle, it does not have to be super accurate, but it knows that there are some 3D geometry in the thing. And on the other hand, we see that the GIGA supervision actually ignores some of the part of the thing that's less relevant to the grasping task. For example, the bow. If we're training 3D reconstruction, it learns to grasp the bottom of the bow, but it is not a graspable part. So when we trained the jointly, it was not like a grasping that bottom part of the bow. So that's GIGA, what we learn from it. Right? So we use this idea of a joint learning affordance and the 3D reconstruction to develop a state-of-art performance in six-off grasping. And as object representation, it has the following properties. First, this is task-dependent, meaning that the object representation is learned from a downstream task for optimizing the graph success. So as a result, the learned representation actually dynamically allocate its representation resource to the part of the things that's most relevant to the task. And we see from the 3D reconstruction result I showed you earlier. It is multimodal. It tries to capture a different aspect of the object properties, like a 3D shape versus affordance, and it captures the synergies between these two. Right? So learning affordance actually improved the 3D reconstruction on the graspable part, and conversely, doing the 3D reconstruction helps grasp in those partially occluded area. It is structured. We combine this conventional, explicit structure of a volumetric feature grid with this implicit neural representation based on neural fields. And the entire object representation is self-supervised, meaning that it's learned from the embodied interaction of the robot by doing this kind of trial and error with a grasp candidate without any human supervision.
I think
Jeanette?
Some questions. Yeah, so this is really interesting work. I'm wondering, the affordances, are they influenced by the context of the scene as well? At all, or is that not, or are these objects basically treated individually?
So the question is if the affordance is affected by the context of the thing, yes, because we are querying this local feature by pulling the representation from the neighboring feature grid. It actually takes into account the context information in the neighborhood.
Right, so that's why this example of the small bottle, for example, being picked first in that initial video that you had. Yeah, and then I was wondering, I guess there are lots of works out there that do pick and place, right, from clutter. And it's really hard to compare them because of maybe different data they are using or just hard to reproduce them, right, locally. So how do you because you talked about state of the art, and I'm wondering, like, how do you kind of encompass all this landscape of work to?
Great question. How do we do like actual proper benchmarking? Right? So here, most of the quantitative results we report and actually based on simulation that we use the same simulation as the prior work, and so that we can make sure that we have the right, the standardized like protocols. Yeah, doing real world evaluation, as you can imagine, is a lot harder to standardize based on different settings, hardware, objects, and lighting conditions, and all those. Yeah.
And so you train on sim data. Do you have any sense of the sim to real gap here?
When it comes to grasping, sim to real transfer is easier when we are using depth information. Actually, we use TSDF as the actual process depth information that really narrows like domain gap, that allows zero-shot transfer with some kind of proper data augmentation, noise injection. If we're doing semantic grasping with RGB, rendering will enlarge the domain gap, right? So that will make the transfer harder. So I think that's what requires new tools and better rendering, better data augmentation techniques to further close the gap.
Okay, yeah, thank you.
Yep.
I was curious, maybe a similar question. Right now, this is all with the parallel jaw gripper. Do you see, like, this would easily extend to much more complicated grasping, like hardware, or would it be very hard because of the simulation challenge of that?
Yeah, so the self-supervised procedures and allows, as long as you can like sample random grasp with like the other morphologies. But as you can imagine, if we're moving to dexterous hand, like so sampling valid grasp with like complex morphology, or we're dealing with like much higher dimensional action space, right? So that's what could potentially create difficulty. So we'll need a better pliers to make sure that we actually sample valid grasp with different robot hardware.
Are only composed of graspable and movable objects. I'm wondering, like, what will happen if there are immovable parts? For example, if there is a shelf in the scene.
We haven't considered that. We assume that all the small objects are movable. Yeah.
How would that affect the learned, like, 3D reconstruction as well as the affordance view?
Well, I can imagine if we really have like environment fixtures, and once you sample random grasp there, it will give a negative affordance label. So the network might be able to figure that out, but we haven't tried that. We assume that all the objects are graspable from now. Get there?
Do you like measure anything like out of distribution?
Yeah,
objects?
So like the good question. I mean, if you look at the results, simulating deformable objects is really hard, right? So and we are using a rigid body simulation. It's really expensive to simulate the deformation in general. But you see that the model was able to kind of grasp the deformable object. And all the objects here are not in the training set because just some random objects that we found in the lab. Yeah, so I have a decent performance on generalizing to unseen objects. Good question. Okay. So that's GIGA. So it's kind of encouraging that we see that this object representation can be learned from embodied interaction. Right? So it kind of motivates us to take a step further to think, can we actually use these interactions to build models of the object that capture the environment properties that's independent from the interactions? See, look at these two objects, and if I try to pull the door and imagine like how the door will move. All right, you can sort of guess it and based on your prior, but it's only until like you pull them and you see that they are actually quite different kinematic structures, right? One is a revolute joint, another is a prismatic joint. So it's kind of interesting to see that whether we can observe the physical interactions of the objects in the real world and use that to create evidence for us to learn the objects and create digital twins. By digital twin, I mean the virtual copy of the same objects in the real world so that we can spawn them in virtual world for physical simulation, and in the fashionable languages, uploading those physical objects into the metaverse, right? So that's kind of the settings that are interesting. The concrete approach, similar to the structured implicit representation we use in GIGA, we use that to process the input point cloud before and after the interactions. And we call this approach Ditto. That stands for digital twin of articulate objects. If you play Pokemon, you know what Ditto is. Okay, so it outputs the part level geometry and and also like a 3D segmentation of the parts, and also the articulation parameters. So just to illustrate how the workflow looks like. So it starts by taking the like point cloud observations from the eye-in-hand camera, and then it can interact either by human or by the robot, and then look at the scene again after the interaction. This gives us the evidence to create this interactable digital twin. By interactable digital twin, we mean that it have this object segmentation, geometry, and articulation properties in place so that we can actually represent this object in some standard 3D format that we can import in a physics engine for simulation. And for Ditto to work, it does not assume that we know the object category a priori, and also it works on two types of drawings, like prismatic versus revolute. So why do we care about digital twin? Is that this type of digital twin recreation actually paves the road for us to narrow the reality gap so that we can observe the interactions of our physical objects in the real world, and then use this to recreate the same object in physical simulation. And the reason we like simulation is because we can leverage like a data-driven technique, generate like a very huge amount of cheap data to train robots to learn manipulation behaviors with this object. And here we are using a simulation framework that we developed in my lab called Robot Suite. And then we can take the manipulation behavior back to the real world for execution, right? And then this new manipulation behavior further like generate new sensory stimuli for us to learn more knowledge about the object. So overall, the Ditto gives us a way to build interactive models to learn the invariant property of objects like from embodied interaction. And we show, again, that being able to physically interact with the object emit new information for us to better understand like different aspects of objects. And again, we show that this structured representation allows us to jointly encode different object properties like their geometry and the articulation. And again, the idea of creating digital twin allows us to kind of like bridging the simulation and the real world in a tight loop so that we can go from real world to simulation and back to the real world through this digital twin creation. Okay, so that's the kind of the first part. I thought I should probably stop here and see any questions.
I think, wait, let me turn on my microphone. Maybe I blinked or maybe I missed it, but where was the model, how you did the digital twin creation? Like I was just wondering about, okay.
I haven't
Thank
showed
you.
the model.
Like I guess I blanked.
Yeah.
Or maybe you didn't show
So that's kind of a technical detail I didn't go over. It does some kind of point cloud processing, use some cross attention. The key is really establish correspondence before after interactions, right? It's how the point cloud moves.
Okay.
And then we use this to decode with this implicit neural field representations. Yeah.
Okay. And so the articulation decoder, how do you assume like a set of possible mechanisms, like a prismatic and a revolute joint?
We assume there's two, and there's first a classification to determine the type versus like it's a binary classifier, and then based on that we have another decoders to output the actual parameters under that articulation type. Okay, great. Thank you. Okay, so now I finished talking about object representation. Let's move on to scales. All right, so what is scales? So scale is highly ties to the notion of a compositionality. So compositionality is a mouthful word, but it's also a very hot topic these days in machine learning. And many machine learning researchers believe that capturing the compositional structures of real-world phenomena, let it be language or videos or robotics task execution, is really the key to achieve systematic generalizations with modern machine learning tool. So a lot of the seminal work in compositionality come from language and logics and the semantics, which they investigate how the sentence of the meaning of the sentence emerge as like a composition of a bunch of words in it. And drawing a parallel, we like to study compositionality in the context of robotic execution. Think about a task like preparing dinner. How can we gradually break that down into subtasks like washing dishes, cooking food, and then further decompose into like a more primitive actions like picking, pushing, grasping. And we call this bottom level constituents of the behavior as like sensory motor skills. So these are grounded on raw perception that are temporally extended, so with temporal abstraction. So if you look at compositionality, and the philosophers and mathematicians, linguists have spent a lot of time like understanding what are the principles of a compositionality. So looking at those really gives a lot of insight. So overall, there's kind of two ways of looking at this. One is the context principle, saying that the meaning of the word hinges on the context of the other words like surrounding the word in the same sentence, right? So the exact meaning of bark kind of like it depends on there's the yellow dog bark at the cat, right? So the yellow dog and the cat kind of like influence the meaning of the bark. On the other hand, there's like the compositionality principle, saying that the meaning of the sentence is a function of its individual parts. In that case, like dog, cat, bark have their own meaning, and when we piece them together, that can like give rise to the meaning of the sentence. So which one is correct, which one is wrong, this is still open debate, right? So we're not going to argue which one of the compositionality principle is truth. But instead, we're going to leverage these two principles and investigate it in the context of compositionality in the robotics context. So this leads to our work first, BUS, which stands for bottom-up discovery of sensory motor skill. That we start with a bunch of like unstructured task demonstrations, where the goal is to extract these words from the sentence. And the drawing analogy here is going from the task demonstration to a set of sensory motor skills that we can use as building blocks to synthesize like a long-term robot interaction to solve a new task. And once we have this library of skills, we can compose them with a meta controller to synthesize long-term interaction. And we want this to be realistic and deployable to real hardware. So we want to make sure that this work is scalable. We do not require human temporal annotations, and the skills operate on raw sensory data. So concretely, how BUS work is first by building a hierarchical representation of a task demonstration. It goes from the bottom all the way to the top by recursively group like a neighboring temporal segments into one based on their similarity, where the similarity is measured by some multi-model or multi-sensory statistics. So we go all the way to the top and apply this agglomerative clustering procedures. And from this hierarchical tree structure, we can extract the recurring temporal segments. So these are the temporal segments that keep repeating in your data sets, and then we use them as the training set of skills. So to illustrate the workflow, we have the temporal tree structure that we extract the temporal segmentations, and then we compute some feature representation of those individual segments. And we pull together like all the temporal segments from like the task demonstrations in our data set, and this demonstration can be collected for like a variety of our task goals. And this allows us to map the robotic behavior into the latent space that we can do a clustering procedure to identify the different partitions of the behaviors in that latent space. From this gives us like a training set for K different skills. Like if we are running a K-mean clustering and that partitions the space by K copies, and then this gives the data sets for us to train for K sensory motor skill that we can actually use the data for goal conditional imitation learning to train these skills. And once we train that, we can compose this with a meta controller to invoke the skill by like predicting the skill ID, like which skill to invoke, as well like setting the sub goal for those skills to achieve. This way allows us to like invoke those skills to solve tasks. And when we train the meta controller, and again use some like a supervised imitation learning objective that we can learn from a data set without trial and error. So to show this actually gives like a quite capable like a solutions to learn like sensorimotor controllers to solve kind of reasonable long horizon tasks that if you don't have the temporal hierarchical modeling, it's really hard to struggle to learn. And the entire model is trained quite efficiently with handful of demonstration collecting 30 minutes of time. And there's kind of interesting observations from this experiments. First, we show that by grouping and building this hierarchical task structure based on multiple modality or like a multi-sensory cues, like multiple views of images and also the proprioception, it actually leads to better task and skill segmentation, right? So this allows us to discover better skills to be composed and for solving tasks. So this kind of resonates some of the seminal study in event perception. A lot of work are done here at Stanford, like by Barbara Travetsky, that so human actually leverage this multi-modal cues and to perceive the boundaries of events. And we show that by discovering and learning those skills from multi-task demonstration, although those demonstrations are not necessarily collected for the same task, by kind of identifying these recurring patterns and train on those data, they actually give rise to more reusable, more generalizable skills, so that they leads to higher task performance compared to skills if are only like discovered from the task-specific demonstration. And also, because like the skills are discovered for multiple tasks, and they have the good versatility and generalization, that we can reuse them for novel tasks by freezing the skills as APIs and only train a high-level meta-controller to invoke them in a new combination to solve new instance of tasks. And to show you how this works, as we said that we want to put minimal assumptions so that it does not rely on human manual segmentation, and collect in 30 minutes of demonstration, we are able to train the robots to perform this long horizon task on the real robot. So everything was done from ground up, from images and to the motor control with imitation learning approach. So that concludes BUZZ, right? So it's a bottom-up approach to discover a set of reusable skills from task demonstration. We show that leveraging multi-sensory cues and being able to discover the skills from multi-task demonstrations and improve the diversity of data. And as a result, by training those, it improves the quality of the skill. And by exploiting this skill and the meta-controller type of a hierarchical design, it gives rise to a sample-efficient learning algorithm to learn complex behaviors using handful of demonstrations. Okay, so take questions.
Clustering in the feature space, or like was there a lot of tuning required, or was it easy to find very different clusters? How much did that have an effect on the end goal?
Good question. So for the clustering, what we do is for each of the temporal segments, we compute a feature based on some multi-model representation learning. Actually, the exact work is what I did with Jeanette and with Michelle Lee and Jeanette in the ICRA 2019 on how to learn like a self-supervised multi-model representation. We use this representation as some signature of the temporal segmentation, and then we group them. So the grouping, actually, we are using a classical, like a clustering method called hierarchical agglomerate clustering. It's a pretty simple method. Just find two closest, like a temporal segments in the neighborhood, and then combine them into one. But the exact algorithm that we use is kind of orthogonal, right? So if we have a better clustering algorithm, then we can plug that in our framework. And in the paper, we actually compare with like different choices, like k-means versus spectral clustering versus this, and this is the one that is the most effective in the setting.
Maybe
Jeanette?
related, like a follow-up.
Mm-hmm.
So you have this representation and you do this unsupervised clustering, I guess, right? But is there any, what is the supervisory signal at the end to say like, oh yeah, that's a good cluster, or is that not? That kind of supervision signal, is that not there?
Yeah, so there's no human supervision, which means that the discovered, there's a give and take. If you are doing unsupervised completely, there's no guarantee that the discovered skill actually carry like semantic meanings. But the reason that it was able to produce sensible segments is because that in a manipulation procedure by looking at like the multisensory statistics, and it can actually give some hints on the structures of the task. If you're doing like so pack insertion before and after you touch the pack, right? So actually the correlation between the like multimodal sensory data changes like in its like statistical pattern. So by using this multi-sensory contingencies, and that is like the kind of supervisory signal there we are trying to harness to build this consistent task structure.
Okay.
Yeah.
And how do you pick K?
Again, a good question. So that's a hyperparameter we choose, right? So somehow in the paper we said 6 is the best. So we have a cross validation, and it was kind of a bell-shaped curve. This I think is like a problem dependent, like based on what is like the diversity of the task and also like the complexity and so forth. So yeah, that's a hyperparameter to change. Okay, so that's the first part of the compositional modeling, and back to this slide on compositionality in language and the behaviors, right? So what kind of Buzz was doing, it kind of resonates with like the context principle, saying that we first give you a bunch of tasks, and I want to extract the skills as like the kind of the building blocks, like the basic constituents of the tasks. So you can imagine it's like drawing a parallel to like from sentences to words. So now we are like looking at the opposite direction. If we are provided with a set of like skills a priori, like a reaching, grasping, pushing, can we use as the building blocks to scaffold like long horizon and complex robotic tasks? So that leads to MAPLE, which stands for Manipulation Primitive Augmented Reinforcement Learning. So in MAPLE, we already given a set of heterogeneous library of skills. The reason we call it heterogeneous is because this skill might operate at different temporal resolution and take different arguments to instantiate their execution. For example, grasping can be a skill, right? So the way we call grasping as functional APIs, we specify the grasp center and the gripper orientation. Why this is a good idea to use like skills? Well, if we're doing reinforcement learning, there's other world of robotics that has been spending decades of research building special purpose robotic behavior modules, right? So there's grasping, there's motion planning, there's like a dynamic movement, like a primitive, etc. So can we actually take advantage of this decades of research in robotics and to use that as a building blocks for behavior? And these modules are typically very well understood, they generalize well, and they have like good performance guarantee. So that's the key idea. But one special thing that we did is that what if the libraries that we build is incomplete? It cannot express the entire space of possible robotic behavior. So we add an additional token or additional primitive called autonomy actions. That's typically what reinforcement learning algorithms use as their action space, right? So to fill in the blank in case like some behavior cannot be expressed by the rest of the library. So that's the key idea that we train reinforcement learning. Now we use this library as the underlying action space. So the policy actually outputs the primitive type and also the parameter, the arguments to instantiate those primitive. And then we execute this primitive to interact with the environment. And then once the primitive finishes, and it returns back the observation and the rewards, and so that we can move to the next stage of decision making. When we do that, we kind of implement a hierarchical policy that first select the primitive, and under that primitive, and the way determines the argument. The whole thing can be trained end to end with some software act critic based method. So to kind of illustrate the idea, we kind of compare MAPLE with a bunch of baselines, and you can find more in the paper. We first showed that atomic action, if we're just using the like bare metal low-level control, and it won't succeed. There's really struggles for the exploration challenge. And compared to MAPLE, we show that it's also necessary to include those primitive atomic actions, because if I'm doing pack insertion, there's a certain phase of the task that requires some really context-rich interaction, like the insertion phase, right? So it needs some very precise and dexterous manipulation behavior. It's really hard to model in the primitive that we have as limited. So we see that it was able to invoke those atomic primitive to fill in those gaps. And actually, we kind of, by composing those primitives, and the Maple unveils the innate compositional structure of the task. So by analyzing the execution, what the primitive is select each time, it can actually build this kind of Wordle-like task sketch. Any of you playing Wordle? So you know that there's squares means the type of primitive is selected each time. And then we can just try roll out the policy under different initialization. And then this kind of generate this what we call a task sketch as the scaffold, as some kind of a signature representing the kind of the structures of the task. So why are we interested in that? Well, for example, like this pack insertion task, we see that first it involves the grasp primitive to first pick up the pack, and then it called reach to try to inch forward and towards the hole. And then in the insertion phase is use the atomic actions to actually does the insertion. So by analyzing the task sketch and under different instantiation, different randomization, we can actually have some kind of quantitative sense of the compositionality of the task. That's actually what we did, for a variety of robotics manipulation tasks, from simple lifting, stacking, pick place, to more contact-rich ones like assembly and insertion. That we see that it makes kind of intuitive sense, for block word and stacking, picking place, and often the case is only the high-level primitive, like a picking, placing, and reaching are invoked to fulfill the task. And the task sketch has a very good consistency across different randomization. But for more contact-rich and tasks that require physical interaction, often the case we see that it's a lot more variable in terms of the task structure. And another benefit of using this primitive is that it can effectively abstract away a lot of the low-level dynamics mismatch between simulation and the real robot if we have a good implementation of a grasping module or motion planning module, right? So we can effectively train our models in physical simulation and then deploy that in the real world. So this is, in both domains, we are using a pose estimator first to detect the object pose. And empirically, often we find that transferring a pose estimation model from simulation to real world with aggressive randomization is a lot easier than transferring an end-to-end policy, right? So by doing this and training the policy on that like a 3D pose, and it allows us to achieve this real robot transfer. Okay, so to conclude this, we talk about how can we use a heterogeneous set of primitives to scaffold the long horizon robot manipulation. And the idea is to develop a hierarchical policy that selects the primitive from the library and instantiate its behaviors by specifying the arguments of the functional APIs. And we show that by doing this, we can analyze the innate structures of the compositional structure of the task, contingent on the primitive we have. Of course, the more primitive we have, and it's likely to change our compositional representation of the task. Depends on the versatility and reusability of the task. So these are the 4 works that I covered so far, what we learned. Okay, so we first talk about what is the skill, what are the object representation that we want to learn. That I talk about GIGA and Ditto, showing you that the object representation we care for fulfilling robotic tasks are often context-dependent and task-dependent, so we can actually learn effective actionable representation from downstream task supervision. And it's often a good idea to capture the multimodality of the object properties and the multifaceted, and very often we see synergistic relationship of understanding the object from different perspectives. And we show that embodied interaction with the objects and is a powerful source of supervision that allows us to learn this perceptually grounded, action-informed information from the interaction. And what is a skill? We investigate the context principle versus compositionality principle. One is going from task to skill, another is the opposite direction from skill to task. And we one of the key property to build effective skill is their expressiveness, their versatility, and also their reusability in different contexts, in different tasks. And one of the key here is to build temporal abstraction to reduce the challenge of modeling the low-level actions, and the fun is the granularity. And also we want to make sure that the learned skills are perceptually grounded, that can operate on raw sensory data. So to kind of put this in a bigger scope, remember at the beginning I mentioned so how do we combine the engineering principles and to modern robot learning approach? That to achieve this, I argue that we really need to combine the methodologies from different views and historically on building AI architecture for robot autonomy. So in the classical pipeline, naturally we are embracing the principle of abstraction, right? So we divide this entire stack of pixel torque into a separate problem of perception, planning, control. There's vision community work on perception, planning community work on planning, control community work on control, and they don't really talk to each other. And what the problem with this is it creates this information bottleneck between the modules, right? So there's going to be compounding errors throughout the stack. And deep learning essentially throughout the stack and replace this with an end-to-end trainable neural network, but we start to see limitation on the high data requirements and also limited generalization. I think a promising new frontier is really kind of combine the complementary strengths of different ideas, right? So while we can still use the kind of rich structured priors and inductive bias in individual learning modules, like the perception, planning, control as the individual functional decomposition of the stack. But at the same time, we can couple them together with object representation, the skill representation, as the state action abstractions, so that we can enable full stack optimization. So that's the vision we are going forward, and I'd like to acknowledge my students who are doing this amazing work for my talk, and happy to take more questions.
Thank you, Yuke. Are there any questions, either in the room or in the Zoom room as well? If you're on Zoom, you can unmute yourself and ask a question if you like. Prayas.
So something that was very exciting was in the second half of the talk, the first part of that you showed with the buds that you were getting 70% success on the task, and that was really good. And then in the next part you showed 100% success on the peg insertion task. So do you think that it's clear from the way you presented that bringing these two things together should really improve task success, but is there anything missing, or is it just like maple plus buds and you're done?
Is maple and plus buzz is done? Not really, right? So, and I think there's definitely things that we are simplified a lot in terms of object variations. Like you are seeing that we are evaluating maple on a lot of simulation environments. The visual stimuli is still quite simplistic compared to the real world. I think so when we move to actual real world settings, we need to bring better models to process on the vision part as well. So definitely just combining these two is not the end of the story. And also, how do we actually build models that can continually interact with the environment, discover new skills, and keep adding new primitives and new abilities to the library, right? It's likely that it is not going to be a one-day job. We can this are the complete set that we are done with that. So we need some continual learning, never-ending learning, to really kind of kick in the loop. Yeah.
More questions? Okay, I have one question.
Sure.
Oh, sorry, was there someone on Zoom? No. No. Okay, I have one question. So in the beginning, you showed this engineering paradigm with this telescope and hundreds of people. And then you showed this general robot with 3 people. And you talked about combining those. I'm wondering what happens if you just add more people to this?
Well, in some sense, like adding more people is already tried, right? So it's not that we are lack of manpower in working on those generalist systems. And there's autonomous driving car companies, and in the industry, robotics companies has been also have big teams of engineers and scientists working on that. So, well, people is one aspect of the puzzle, but I think so like a better methodologies and better algorithms and being able to be open-minded and see that as a robot learning researcher, sometimes we hear engineering and the systems, we can that's something that we belittle, right? So that's something that we don't like. That's a sign of incremental improvement. But I feel like being more open-minded and embrace those principles and really look at the problem from the system perspective is the way to go. So yeah, again, it's not just a people problem, but also new method and new insights are needed to enable the next level, take it to the next level.
Okay. All right. So thank you very much, Yuke, for coming also in person to
thank you for
be part of
the
this,
invite. Yeah.
be part of this Stanford Robotics seminar after 2 years. So thank you everyone for coming, and I see you next week on Friday.